Hello. So in this video, we're going to prove that Cauchy sequences are bounded. Okay, and this is one of the lemmas that will be needed in order to prove our main goal from this section, that convergent sequences are precisely Cauchy sequences. So this is another tool that we're going to need in order to prove that result. But first, we need to prove this. So what are the tools that we're going to need for this result? What are the ideas that we need in order to prove this? Well, so the statement is a Cauchy sequence of real numbers is bounded. So we're going to, of course, need the definition of Cauchy. Okay. But then what else? What's the idea here? Why would this make sense? Well, Cauchy sequences, right? After a certain point, a certain index, all the indices after that are kind of jumbled together, right? That was kind of described in my video on what are Cauchy sequences. So wouldn't it make sense that after a certain cutoff, all the terms are kind of close together. There's only a finite number of terms outside of that cutoff. And then all the cutoffs are close together. How could it not be bounded, right? So maybe the idea is to make a bound on the sequence by splitting it into an infinite part and a finite part. An infinite piece and a finite piece. Since the sequence is Cauchy, that infinite piece that we're talking about are the pieces that are all jumbled together, right? So then we can maybe take a absolute value of the maximum between the distances of the infinites, and then we have all the other pieces which are just like finite, right? So maybe one more idea that we're going to employ, and you'll see how this works out in the proof, is to fix one index. And I'll point out when I do that in the proof. Okay. So let's go ahead and prove it. Let X be a Cauchy sequence. Okay. Now, if you remember the proof that we gave for showing that convergent sequences are bounded, right? What did we do? We fixed epsilon, right? So in particular, when I say use the definition of Cauchy, we can fix epsilon equal to like 1, right? And then we have like a solid number to work with to bound that infinite collection of terms after the cutoff index when all the terms get close together. So let X be a Cauchy sequence in AB and choose epsilon equal to 1, right? Since the sequence is Cauchy, there is an index cutoff so that after that cutoff, all terms are within distance 1 of each other, right? That's the definition of Cauchy. So I'm just going to state that. Then by definition, there exists say some index h so that n and m greater than or equal to h imply that the distance from xn to xm is at most epsilon. But in this case, we chose epsilon to be 1. Okay. Okay, so now what we're going to do is we're going to fix an index here. So I'm going to say next let, I'll say m naught equal to h, the cutoff index. Okay. And observe that if n now is greater than or equal to h, then applying the triangle inequality, the reverse triangle inequality, again, m naught is equal to h, and since this is bounded above by 1 for all indices greater than or equal to h, I can write that this is at most 1. Right? But this implies, so thus, if we add x of n not on both sides, we get thus the absolute value of xn is at most 1 plus that term, right? And this has to hold for all n greater than or equal to h. Right, and that's just some number, right? That's a fixed index, and the sequence just gets mapped to some number. So what we've done is we've bounded an infinite portion of the sequence all above by that, right? Now there's only a finite number of terms other than that, right? All the terms with indices strictly less than h. So I can say maybe by, by the completeness property, of R, right? Every bounded set of real numbers has a supremum and it exists in R. So by the completeness property of R, we can say that the following number exists in R. So by the completeness property of R, I'll call it M equals to the sup of x sub 1, absolute value of x sub 1, absolute value of x sub 2, dot, 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 absolute value of x of m naught minus 1. Right, that was the cutoff, right? H, m naught is equal to h. So that's the finite portion there. And then the other bit is bounded above by that. So by the completeness property, this exists in R. and absolute value of xn is at most m for all natural numbers n. Hence, the sequence is bounded. Probably should have, let's end the proof, but I probably should have wrote that over here in my tools, that I needed the definition of being bounded, but that is the definition of being bounded. The absolute value of each term is at most some fixed real number m for all indices n. Okay? So in the next video, we're going to finally prove the major result from this section. That is that convergent sequences are Cauchy sequences. And Cauchy sequences are convergent. Thank you.